Okay, hello and good morning everyone. My name is Amir. I think it's time now to start this webcast. So do we move optimally? This is the question of today. And I'm very happy to have Dr. Saeed Farahani from Aalborg University next to me. And he will give a presentation today about prediction of human movement by musculoskeletal models. And he will tell us if we move optimally or not. About the outline from today. I will start first to talk a little bit about who and what is anybody. Then I will hand over the microphone to Saeed and he will give his presentation. And then afterwards we will have a live questions and answer sessions. This brings me to the following points before I get started. This webcast will be recorded and we will put it on YouTube later on, as well as we will hand out this presentation as a PDF. So everyone who joined us today will have the chance to look again at the webcast or to read again at the webcast if you didn't understand anything correctly. On the other hand, you have a little window here where you can type in questions. So please feel free, whenever you have a question, type it in there. If it's about something technical about anybody, or if it's something technical, something related to the models that Saeed will show us today. So you can type in the questions and either we will answer immediately or then we will discuss those questions at the very end together with Saeed. So very briefly, what is anybody? Or let's start with who is anybody. So there's Anybody technology. This is where I'm working. This is the company that develops the Anybody modeling system. We provide licenses, training, support, and we do consulting projects in the field of biomechanics. And there's also the Anybody research group of the Aalborg University, headed by Professor John Rasmussen, and he has several researchers there as well, and he's doing research in the field of biomechanics, orthopedics, ergonomics, gait, and many other things. And this is also where our guest from today is coming from, Saeed. So he will talk about his studies of the last years today. So in general, anybody can be found in many different areas. So if I start on the top left side, you can do work environment analysis. You can look at assistive devices for work. If you go then to the top, Anybody is used in the product design optimization. So, for example, if you want to optimize a wheelchair so that it has the best geometry in terms of ergonomics. And the automotive area, it's also very often used for ergonomic analysis. And then in the orthopedic field, it's used for surgical planning, evaluation, failure analysis, and also to export physiological loads into finite element studies. Anybody is a musculoskeletal simulation software, so we use activity or motion as input and muscle forces, activity as output. And we have a full body model with bones, joints, muscles, and ligaments. The principle that is used here is called inverse dynamics. So once again, input is motion, output is muscle forces, joint reaction forces, and also some interaction forces. On the right side here, you see some details of this full body model that we have. So roughly, we have about 1,200 muscle fascicles in the full body model, and you see also some details like lumbar spine, foot, knee, hip. So some of those detailed segments have been developed in several man-years. The typical application is you load basically an activity into the modeling system and then you analyze muscle activities, forces, joint forces, etc. You can also do a more advanced workflow, so add patient-specific or subject-specific information from CT or MRI scans and then export everything into a finite element model, so there are interfaces to Abacus, to ANSYS. And there's also an interface to CAD systems. So if you're using SolidWorks, for example, you can export your whole assembly from SolidWorks into Anybody. with all mates, mass properties, joints, etc. And finally, there's also a hook to advanced processing languages or scripting languages like Python, MATLAB, or optimization softwares. But I think this is now enough about anybody itself. So today we have Dr. Saeed Farahani with us. He is a Bachelor of Science in Mechanical Engineering and a Master of Science in Mechanical Engineering, specialized in applied mechanics. And since 2010, he worked on his Ph.D. at Aalborg University under supervision of Professor John Rasmussen. And last year in December, he defended successfully his Ph.D. thesis titled Human Posture and Movement Prediction based on Musculoskeletal Modeling. And here you see a little picture where he got his certificate actually a couple of days ago. So he's now Dr. Saeed Farahani, and he will give a talk today about do we move optimally. So we'll hand over the mic to him now.
Yes, hello everybody, and welcome to this webcast. I would like to thank Amir for the nice introduction. Actually today I'm going to talk about human posture and movement prediction based on musculoskeletal modeling. Actually this project was conducted with the close collaboration of Anybody Technology and Anybody Research Group located at the Mechanical and Manufacturing Engineering Department, Aalborg University. And it's a part of a bigger project called Anybody Inside Project. Okay, this is the agenda for today. Actually, I start with the introduction, which includes motivation, human models, simulation models, and the most important part, which is the state of the art of the project. And then I will go through the steps that we need to predict the human movement, starting with the parameterization, objective function definition, and then optimization and validation. And I will also discuss about the results. Of course, it is not possible to talk about all the results that we have been actually getting during the past 3 or 4 years. So I just talk about 3 cases that we have been involved with. And in the end, I will conclude the works, and then I will address to some future works. Actually, there are many potential applications for the digital mannequins, like in the rehabilitation, orthopedics, clinical biomechanics, ergonomics, and occupational biomechanics, and so on. But in all cases, the digital mannequin must be driven by the experimental kinematic and kinetic data. And we know that doing the experiment is not that straightforward, and it has its limitation, like it is usually time-consuming, technically difficult, and potentially unsafe, and normally expensive. So finding a reliable and computationally efficient method to predict the human posture and movement would be very beneficial for the biomechanical engineers. So today we will talk about this technique. It's called inverse dynamic, and I will show you how it works and what we need to do that. But before I go through the slides, actually I should mention something that in some slides we have very busy slide, and then maybe I very briefly mention some part of it, and then as you will get the PDF of the presentation later, then you will have enough time to go through the details and actually get more information out of the slides. Anyway, let's start and talking that how we could actually predict the motion. Normally, in the field of human posture and movement prediction, there are generally 2 types of models that use. What you see on the left-hand side is a joint torque model, which has 55 degrees of freedom, and actually it's made of series of rigid segments connected by 1 or more revolute joint here. And what you see on the right-hand side is the Anybody musculoskeletal model, which is equipped with several hundreds of muscle, and it has been written in a very general scripting language system. So meaning that you can actually go ahead and define more muscle or ligament based on what you need and level of the complexity of your works. You can actually change the complexity of the model. So In my project, I use anybody musculoskeletal model. But before talking about human posture and movement prediction, we should know that why we need simulation models. Actually, the answer is quite clear, and the reason is that direct measurement of the muscle force as a fundamental requirement for movement study is restricted to invasive measurement. So we should somehow find a way to actually predict the muscle forces. There are two types of conventional simulation model, forward dynamics and inverse dynamics. And based on the availability of the input data, one of these methods can be used. But in these two cases, actually, we are facing the redundancy problem. It means that we have more muscle than what we need to generate the motion. To address this problem, usually we use optimization. It means that by minimization of an proper objective function, actually we could cope with the redundancy of the muscular load sharing. Very briefly, I will talk about the forward dynamics. As probably most of you know, it starts with the muscle activation, and then we calculate the muscle forces, and then the muscle forces are input for the equation of motion, subject to the kinematic and kinetic boundary condition, and also external forces and moment. We will be able to calculate the kinematics. In inverse dynamic, the formulation is reverse, meaning that we start with the kinematic data, and then we go forward after kinematic analysis and forming the equilibrium equation, we will get the muscle forces. But as you see in both simulation model, we need the input to get the output. And without the input, we will not be able to actually calculate the output. But we should know that in many practical simulation cases, neither the muscle forces nor the motion is known a priori. So that's the idea and reason behind this project, that why we need to actually predict the human motion. So here you can actually see the research questions that I'm going to answer them. The first question is that, can we resolve the indeterminacy by formulating the human movement as an optimization problem? If we could answer to this question, then the next question would be that what the objective function is. And then in the end, does any single formulation predict wide range of human posture and movements? So I will talk and I will answer to this question. Let's start with the classification of the different approaches in the field of human posture and movement prediction. There is one approach is called the phenomenological approach, which is basically based on the experimental data which is collected in the lab, and then we do the statistical analysis, and then we make a statistical model using, for example, the regression model, and then we could actually predict the motion which is similar to the one that we actually collected the data in the lab. Another class of the approaches are optimization-based approaches. Again, depending on which simulation model we use, if we use a forward dynamics model, we will have the forward dynamics-based formulation, which is called optimal control. If we use the inverse dynamics, then we will have inverse dynamics-based formulation. And depending on the model that we use, actually, again, we have two general categories. If we use the joint torque model, then it's called predictive dynamics in the literature. And then if you use the musculoskeletal model, then actually we would like to call it inverse dynamic. And this name actually was chosen by John Rasmussen in 2001 in his first study about human movement prediction. If we would like to talk about the novelty of the inverse dynamic, I would say that we somehow generalized the idea of using an inverse dynamic-based formulation for human posture and movement prediction by using a detailed musculoskeletal model. Okay, here you can see a very abstract flowchart showing the inverse dynamics idea. So what we do, we start with the parametric kinematics, and then we actually, after kinematic analysis, we will form the equation of motion, and then we calculate the muscle sharing problem by solving an optimization problem, and we will get the muscle and joint forces. And then here we evaluate a user-defined performance criteria. And according to the result that we get and out of the evaluation, we should update the design variable. And then after many iterations, actually we will find the optimized value for the parameter of the parametric kinematics. So as you see here, we have one optimization loop here to solve the muscle sharing problem, which I would say it's an inner layer optimization. And then here we have an outer layer optimization, which is used for the movement prediction. So if you want to put it in a mathematical formulation, you see that in the optimization problem, the optimizer will find Qi, which is the design variable or control point, which controls the kinematics, which is the input for the loop here, in order to minimize the performance criteria, subject to these constraint here. The first constraint is the anatomical joint angle. So each joint angle should be within the acceptable range and anatomical range. And the muscle strength, as you see here, it should be positive. It means that all the muscle can only pull, they cannot push, and also they are bounded by their maximum strength during the working condition. And also dynamic stability, obstacle and self-avoidance, and environmental constraints are the list of the constraints that should be actually entered into the optimization problem. The first step to start and predicting the motion is to parameterize the movement. The joint angles should be parameterized by means of a time function controlling the motion. There are several ways of doing that in anybody. We could use B-spline, polynomial, or Fourier series. So here is just an example of a joint angle which has been plotted against the time. So these red dots here are the design variables or control point, and these dash blue line here is the B-spline. So as you see here, each red spot can be actually varied during the optimization in order to find the optimum pattern for that specific joint. But we should notice that number of design variables or control points significantly influence the computational time. And identification of the level of the parameterization complexity remains a challenging task. So we don't know actually for a specific that how many control points we need. So that's one challenging task. And another thing that should be noted is that the machine parameters can be considered as design variables in the optimization problem. The next step would be actually definition of the objective function. As I wrote here, the optimality hypothesis in human movement prediction is that movements are planned to optimize the performance criteria. So everything after parameterization depends to the performance criteria. So we could actually categorize the objective functions into big category: hypothesis-based objective function and performance-based objective function. In the performance-based objective function, we are almost sure about the objective function. For example, in kicking, we are trying to minimize the time. In throwing something, an object in the air, we maximize the distance. And in vertical jumping, we try to maximize the height of the center of mass. But in the hypothesis-based objective function, we don't know yet what the proper objective function is. So actually, we should somehow hypothesize the objective function. Again, it could be kinematic-based, or it could be dynamics or physiology-based. In the kinematic-based, as you see here, here are some typical examples of the kinematic-based objective function. But the problem with the kinematics-based objective function is that you cannot take the external force and moment into account. So, so the predicted result when we have the external load will not be that realistic. So in order to take all the external and dynamic forces into account, we would use the dynamics or physiology-based. Again, depending on the model that we use, if we use the joint torque model, then the objective function can be defined based on the joint torque or normalized joint torque. So you can easily find these typical cost function in the literature. Or if you use a musculoskeletal model, the objective function could be defined based on the muscle force or normalized muscle force. The third step, which is very, very important, is the method that we should apply and use for the optimization. Actually, we prefer to use a complex method, which is a non-gradient based optimization technique. And very briefly, I explain how it works. Actually, if we imagine that the small circle in the middle has the minimum value for the objective function, and the maximum value is circle number 1, we start with some initial guess. So with this 3 point, which is called design population, and then obviously this point has the worst point, so which has the higher value. So this point will be mirrored respect to the centroid of this point. So we'll get a new point here. And then if we continue and go forward again by mirroring the worst point respect to the centroid, then we will converge to the solution, which is the small circle in the middle. But what I should mention is that this method is originally an unconstrained optimization technique. It means that if I run this video here, you see there is no constraint, and then it has a evolutionary actually approach, and then the points will get converged to the solution here. But what we need actually in the human movement prediction, we are facing with a constraint problem, and the search domain here in most cases is a non-convex area. It is like this donut shape that you see here, and then the design population could be inside this non-convex area or out of it. But by using the penalty functions, we could actually convert the unconstrained problem into the constrained problem. If I run it, we will see that definitely the answer is somewhere here. So we will use the penalty function to actually handle this situation. And in the end, when we run the optimization and we get some result, we should be able somehow to actually quantify the error. What we use here, we use a Gears metric, which was proposed by Gears in 1984 to quantify the differences between the predicted and measured result. So we have 3 major parameters, capital M, P, and C. M is the magnitude error, P is a phase error, and C is a combined error. And then as you see here is in the Gears metrics, it's integration-based formulation for the error quantification. And then if the experimental data and computational results are identical, then M, P, and C will be 0. So the more close to 0, the better result actually we have. Okay, now it's time to answer the first research question. Can we formulate the human movement prediction as an optimization problem? To answer this question, we should start with an example that we are almost sure about the objective function. And if we get a good result and in agreement with the experimental result, then we would say that yes, it could be possible to formulate the human movement as an optimization problem. So here we have a squat jumping model. I call it SVG, and here I have another model together with the arm, which is called squat vertical jump arm swing with arm swing. I call it SVGA. So this is the actually predicted motion as you see here, and then I will discuss more about the kinematic and kinetic data that we get out of optimization. And then here is the same model using the hand, because we are interested to see how the arm swing can enhance the jump height as well. So we start with the model, and actually we parameterize the motion. What you see on the left side is a squat vertical jumping model. So the foot actually is attached at the metatarsal joint using a spherical joint to the ground. And what we choose the ankle angle, knee angle, hip angle, and pelvis thorax extension angle here. So we have totally 4 angles for the squat vertical jumping with the closed arm. And what you see on the right hand side is squat vertical jumping with the arm swing. So we have to parameterize the elbow angle and also 3 shoulder angle. So and then in each case we use 12 control points for each joint angle to discretize the motion over the entire time. And we use a 4th order B-spline curve. if I want to summarize the optimization problem in the squat jumping, actually we have this objective function here, the height of the center of mass at the takeoff, and also this guy here, which is the maximum the maximum height of the center of mass in the airborne phase. And then so as you see here, the first guy here is related to the potential energy, and the second one is related to the kinetic energy. So in jumping, we are somehow trying to maximize the mechanical energy. And then here we can see the optimization problem. Qi is the design variables, and then we try to find the optimal value for this Qi to minimize minus objective function, which is equal to maximization of the objective function here, subject to the constraint. We did experimental study to validate the result. I don't go to the details. I just briefly mentioned that a group of 6 healthy males volunteered, and then we installed the reflective markers. We used 2 force plate, and then with the 8 infrared cameras in order to capture the motion. And actually, with the subject did the squat vertical jumping with the closed arm and with the arm swing, and they recorded experimental data. They were imported into Anybody modeling system, and after kinematic analysis, we calculated the joint kinematics, and then we run the inverse dynamics to get all this necessary information to analyze the jumping movement, which are the displacement of center of mass, kinematic energy, mechanical energy, joint and muscle forces, joint moment, joint power, and work done by the joint. But as you know, the time doesn't let us to talk about all the results. So here, as you see, what you see here is the selective part of the result that we got. So what you see on in the blue color here on the right-hand side is the result for the squat vertical jumping with the closed arm. So you see the center of mass vertical displacement, center of mass vertical velocity, and the vertical ground reaction force, and also the impulse of the vertical ground reaction force. As you see, in all cases, there is a good agreement between the predicted result, which is plotted by the dotted black line, and also together with the experimental mean with the solid blue line, and this blue shaded area is the range of experimental value. And as you see here, there is a small gap here at the beginning of the predicted result, and we can also see here that in the squat vertical jumping, the predicted jumping time is 0.57, which is less than 0.6, and this could be explained by the fact that we have a one segment foot. It means that the toe segment doesn't contribute in the movement, and the model will leave the ground a bit earlier than what we see in the reality. And then here also you can see the result for the squat vertical jumping with the arm swing. Again, there is a good agreement, and the predicted results, they are all in the acceptable range. And then if you quantify the error, we will see actually the quantified error here, normalized root mean square error, coefficient of determination, and M, P, and C for both cases, SVG and SVGA. In all cases, actually, we have got a good result with the acceptable error value. If you look at the predicted kinematic in the SVGA and SVG, here you'll see that the ankle angle, knee angle, hip, and pelvis thorax extension angle, actually there is a pretty good agreement between the predicted and experimental result, and we see the same in the SVGA. Yeah, if you quantified the error between the predicted and experimental kinematic here for the SVG and SVGA, again, if you look at the normalized root mean square error, actually they have in all cases except this one, we have a very low value for them, and the coefficient of determination in almost in all cases they are very close to 1, and the magnitude, phase error, and combined error, yeah, except some cases, as you see here, the numbers that we got is very close to 0. So what we conclude is that inverse dynamics can reproduce the coordinated motion. But not only the coordinated motion. If you look at the experimental and predicted result in terms of the jump height enhancement, as you see here, you can see the average experimental result here. And then in the experiment, if you look at the experimental result, you will see that by using the arm swing, the jump height will be enhanced for 28.2, and then in our case, the predicted result shows that this enhancement is 26.6, which is actually quite acceptable here. So what we conclude is that this approach is also capable of predicting the jump height enhancement in squat vertical jumping with arm swing. Okay, now we answered to the first question that we can actually formulate the human movement using an optimization formulation. But now the next question is that what is the optimized criteria for a movement under investigation? So if we consider a pedaling movement, actually we don't know how the central nervous system controls the movement. And here we have a model that in this model the foot is attached to the pedal by a revolute joint, and the green arrow shows the pedal forces. And then we would like to see that, as we have only 1 degree of freedom, we would like to see how the ankle angle actually move and what is the optimized value for the crank moment. So to do so, we start with this musculoskeletal model here, and then it is equipped with the heel type muscle model, and then we could be able either to parameterize the pedal angle or ankle angle, because they will be the same because the foot is attached to the pedal. But in this case, actually, we choose the pedal angle, and then we use a Fourier series to parameterize the pedal angle. And what we actually choose, we choose only the first 3 terms of the Fourier series. So what we have totally 8 design variables controlling the pedal angle. Another things that should be parameterized is the crank torque or moment. So this is a typical crank torque which has been plotted against the crank angle. As you see, it has a sinusoidal shape, and then actually by choosing these offset moment here, and also these top dead point crank, and also these phase shift, which is called alpha M here, we could actually have different shape for the crank torque. So what we do actually, these M offset and also frequency F, which will be compiled from the experiment, and then we will let the optimizer decide about the top dead point moment, which is this guy, and also these phase shift. So if you look at the optimization definition, if you look at the, if you want to do the formulation for the pedaling, as we don't know what the objective function is, we actually start with the general form of objective function, and then parameter P and Q in this formulation actually let us know to have a different mathematical form for the objective function, and then we let the P and Q vary from 1 to 5. So in this case we have totally 25 different objective functions to be tested. And then we also look at this max objective function that Professor John Rasmussen, he has actually used this objective function in some movement. So in this case also we will try it to see if it works for the pedaling or not. So here you will see you can see the optimization problem definition. So we have totally 8 design variables. The first 6 design variables will control the pedal, the ankle angle, and then these 2 guys here, M and alpha, will decide about the shape of the crank torque to minimize F, which is the objective function, subject to the constraint that we have. Again, actually we did the experiment together with our external collaborator to collect some experimental data to validate our predicted result. Very briefly, a group of 9 male cyclists volunteered for this test, and actually output power and pedaling cadence were sampled at 10 Hertz using some devices which actually were used for the test. 3 tests on the level train and 3 tests on the uphill train actually were conducted, and so you can actually go through the rest of the text and read it yourself. And then what is important for us is the pedaling cadence, and power output, which should be used as a constant value in the sinusoidal form of the crank moment. So actually, we first look at the predicted result for the pedaling on level train, which is more common. And what you see here, this shaded area is a range of experimental variation, and then this dotted line is the experimental mean. And different colors shows different predicted result for the different values of the Q. And then we also can see the max result here. By looking at the graphs here, we will see that the predicted results is much more sensitive to the variation of the Q and not to the variation of P. And if we quantify the error, this is something that I have already done, but I haven't reported it and I haven't added to these slides here. But we will see that for this case, for P equal to 2 and Q equal to 2, which is this blue curve here, we will have the minimum value for the error. So actually the objective function is much, if I want to summarize it, is much more sensitive to the variation of Q, and for P equal to 2 and Q equal to 2 we get the good results. But we should test this value of P and Q for different actually pedaling condition, like pedaling at the level train at high cadence and the level train at low cadence, uphill train at high cadence, uphill train at the preferred cadence, and also uphill train at low cadence. If we do so, and if we quantify it and calculate the mean value of the errors for different values of Q and P, we will get this shaded actually area that has that shows that for P equal to 2 and Q equal to 2, we have the minimum value for the errors. And what we could actually conclude is that summation of a squared muscle activity gives the good result for different cycling condition. Okay, so in the pedaling movement, we saw that it is not that easy and straightforward to find out what the proper objective function is, and a systematic investigation should be conducted to find the proper objective function. But apparently, an objective function defined based on the muscle activity actually gives a good result. So we should test this hypothesis, and we should answer to this question: that does a performance criteria defined based on muscle activity predict wide range of human motion? To do so, we will look at this crank rotation task here. So here is the musculoskeletal model rotating a crank. This blue line shows the tangential and radial forces during the movement. In order to validate the predicted result in the crank rotation task, again, together with our external collaborator, we did an experiment to collect the kinematic of the horizontal arm movement. As you see here, there is one of the subjects seated on a chair, and then the upper body is fixed by a harness, and then we use the balancer to make sure that the arm actually move horizontally, and then we use a cast here to make the wrist fix, and then we use a force transducer to actually measure the tangential and normal force. And also we use an AC servo motor to provide a viscous torque against the movement. And then here we can see the dynamic equation of motion for the crank rotation task. I is the mass moment of inertia, B is the viscosity coefficient, and capital F here is the hand contact force. Very briefly, 4 subjects participate in the experiment, and different subjects started with at different starting points, and the angular velocity was 0 at the beginning and the ending of the task. Each subject conducted 100 clockwise circular reaching movement and at their own pace. So in order to predict the motion, we made this musculoskeletal model of the subject rotating the crankshaft, and then here the thorax is fixed, and the pelvis also is fixed, and then the handle, the hand is attached to this handle using a revolute joint between the hand and handle. And as you see here, actually we have different starting point A, B, C, and D. Here, this is the rotation direction. And then what we parameterized the angular movement of the crank. Because we have only 1 degree of freedom, so we need only one parameterization. Actually, in this study, we use an objective function, which is basically defined based on the muscle activity. We use the metabolic energy expenditure. In anybody, we have a very simple formulation for the metabolic energy expenditure by the muscle. We have the mechanical power divided by mu. Mu could be 0.25 or minus 1.2. In this case, 0.25, it is actually for the muscle shortening, and the negative value is for the muscle lengthening. And then here is the optimization problem. So again, the optimizer will find the design variables to minimize the muscle metabolic energy subject to the constraints. If you look at the obtained result, as you see here, we have a different starting point A, B, C, and D. What you see here is a crank angle, which has been plotted against the time here. The red dotted line is the predicted result, and the black solid line is experimental mean, and the gray lines are the last 5 trials out of 100 circular movement. Actually, here I have only used or looked at the normal hand contact force, because the tangential component of the hand contact force is directly linked to the movement, but the normal hand contact force is indirectly influenced the movement. So if we could predict the correct normal hand contact force, we could say that actually we have got a good result. So for a starting point A, B, C, and D, you see here the predicted result in dotted red line, and then line, except starting point B, which has not very actually low value for the error, we have got good result. So this result for a starting point B actually based on the experimental setup, we don't know yet if it is because of that specific subject or if it is because of the starting point. So we should look at it more carefully later. Anyway, as we just saw the result, apparently muscle metabolic energy expenditure gives the good result. I would like to go back to the research question that we mentioned in the beginning of the presentation. Can we formulate the human movement prediction as an optimization problem? The answer is yes. The results of the jumping study indicated that human movement prediction can be actually formulated as an optimization problem. And the second question was that what the appropriate objective function is for the human movement. The results of the pedaling study showed that for a movement under investigation, a range of performance criteria should be evaluated in order to find the proper objective function. So that's very, very challenging. So for any actually task, we should do a systematic investigation to find the proper objective function. But what we saw was that actually a cost function defined based on the muscle activity can give the good result. And in the end, does any single formulation predict a wide range of human posture or motion? The result of the crank rotation task indicated that an objective function defined appropriately based on muscle forces could actually predict the natural human posture and movement. And in the end, I would like to address to some future works actually defining a proper optimality criterion to solve the muscular load sharing problem remains a major challenge. And one of the unanswered research questions will be that how the central nervous system choose one of the possible muscle activation sets. Another actually way of for the future works is, although a performance criteria defined based upon the muscle activity seems to be a good choice, of course, more investigation is needed to uncover how the central nervous system governs the human posture and movement for different tasks. And in the end, in order to investigate the capability of inverse dynamics technique, we need to predict more complicated movements like some movement like normal gait or perturbed gait to make sure that it works for the more complicated task. In the end, I would like to thank you for your attention, and then I will direct you to Amir, who is sitting next to me. So thank you.
Okay, thank you, Saeed. Thank you very much. This was very impressive. You have done a lot of work, and you have shown some very interesting results as well. Especially the comparisons with the experiments show that it's very close to reality. So for those of you that thought that this was a little bit too technical or something, or you couldn't follow everything, so there's a paper out from Saeed. We can provide you the link to the paper, of course, and also there's more information. So we will also hand out the PDF, as Saeed mentioned before. So before we come to the live questions, there will be another webcast in 2 weeks from now. It's about a musculoskeletal model of a swine mastication and its clinical applications by Dr. Chad Gordon, Dr. Mehran Ahmad, and Ryan Murphy from Johns Hopkins. So that should be also very interesting. If you want to get in contact with us, there are several options. One on anybodytech.com, where you find some events, how to find us. There's also this publication list with some very interesting papers that Saeed mentioned here as well. We have a technical forum on anyscript.org, and also this recording here, or the recording of this webcast, will be uploaded to YouTube again. There are also some email addresses where you can find us.